All right, here we go. Slide number 7. You see what I was talking about on a fractional compressor, fractional being less than a horsepower, typically on small stuff. Number 7, you got that red cylinder on the side of the compressor. That's an accumulator. Slide number 8, liquid line receivers. So we've already shifted. We're going into receivers now. We've discussed accumulators just a little bit. Again, accumulators accumulate liquid refrigerant and through the aspirator convert it to vapor refrigerant, making the vapor and the oil leave and go to our compressor. Our liquid line receiver is not near our compressor. It's in our liquid line. So we're going to see that after our condensing coil, we're going to have a liquid line receiver. Our liquid line receiver is only going to be on commercial industrial systems. You will not see it on a residential piece of equipment. What are we doing here? We're storing excess liquid refrigerant somewhere other than the condensing coil. If we did not have a liquid line receiver on a commercial piece of equipment, such as a refrigerator or a freezer, walk-in, even some reach-in equipment are going to have a receiver. If it has a adjustable metering device, you're going to see a receiver because that adjustable metering device is going to modulate. It's going to open and close as needed based upon whatever it's based upon because it's adjustable. It could be our suction pressure. It could be our superheat, and that input could be in a couple different ways. If it's an EAV, that input is going to be electronic. If it is a TXV, that input is going to be from the bulb. It is going to feed more or less refrigerant into our evaporator to keep our evaporator right where it needs to be. Well, where's the more and less going to stay? Well, the more or less is going to basically fill up our coil, and our coil will not be able to do what it's supposed to do, which is transfer heat, because there's liquid refrigerant stored in our coil. So we have a receiver that does that. Again, our receiver is located in our liquid line. It's located after our condensing coil. Where is our sight glass and our dryer in relationship to our receiver? Talk about that in just a minute. I think we might have a picture, so I'm not gonna jump ahead of myself as much as I usually do. Okay. So that was slide number 8. Slide number 9, you see a picture of a receiver. On the side of the receiver, again, inlet, outlet. Outlet's important, inlet's important. You need to make sure you keep them separate. On the side of our receiver is a king valve. This is the spot where, well, what's the difference between a king valve and a stem valve? Nothing. One's a king valve, and then I've talked to guys and they'll look at a system and they'll say, oh, I didn't realize it had a king valve on it. They're not wrong. We typically refer to a valve that you can open and close with a stem on it and a valve wrench as a stem valve in this class. The king valve is a stem valve. It's got a stem on it and it can be opened and closed. The purpose for that would be so we can pump all of our refrigerant into our receiver so we can stop the outlet of the receiver through our liquid line, through our metering device, through our evaporator, through our suction line, back into our compressor, out of our compressor, through our condensing coil, out of our condensing coil, and into our receiver. It can't go past the receiver because we've closed, front seated, our stem valve, or king valve is really what we're going to call it. It's on the receiver, it's a king valve. But if it's front seated, it's all the way closed. If it's back seated all the way back, remember, this is, I think, refrigeration 1, back seated, if it's all the way back, it's all the way open. Cracked, we're going to stay in the all the way open. We're going to stay in the back seated position as our home position. We're going to crack it from home to partially open to make our service port active on the side. And then we can read pressures there. That's really jumping back to a stem valve. A king valve can also have a port on it. But that's what's going on there. You'll notice on this slide we discussed 20% for hydrostatic, easy for me to say, hydrostatic expansion. What's going on? If I fill this tank with too much refrigerant, and then that refrigerant gets hotter, it's got to have a place to go. So it's either going to blow out our plug in the bottom, our safety, and then we're going to lose our refrigerant, or we're going to size our receiver such that there's room for expansion within there, 80%. Just like we would on a recovery tank, we want to make sure that when we pump a system down to the receiver, if the compressor labors and it won't fill the receiver, because the receiver is probably too full. So you want to be careful with that. Hydrostatic expansion, just like on a recovery tank, we only ever want to fill a recovery tank to 80% in most of the world. If we're in Arizona, where our temperatures are going to be above 125 degrees, or anywhere where our temperatures are going to be above 125 degrees. When you guys go to Mars and you're working on air conditioners, and it's always above 125 degrees there, you need to make sure you only put 60% of the refrigerant in your recovery tanks. All right? Why? Because we need more room for hydrostatic expansion because it's going to be hotter. And that refrigerant, the molecules in that refrigerant are going to be boogieing faster, and we need to have a safe, and we want to make sure that we're safe. So that's what's going on with our 20% rule there. I've discussed where your receiver is, where your king valve is, and now you've got a picture that backs that up. As per usual, I usually jump ahead of what my slides say. Number 11. Can you name the numbered controls above? Well, look, number 12 shows you all those answers, so I'm not going to spend a lot of time on that. There's your refrigeration cycle. If you'd like, this is the moment where you stop, you get a piece of paper out, and you draw the refrigeration cycle just like I would, and you can explain all those parts and pieces. 13, again, we're naming components. Do we give the answers to these? No, but they're basically the same components. They are the same components as what's in 12. 13 is just a different picture. The one that we don't have on 12 that we do have on 10, I'm not seeing, yeah, we do have a heat exchanger, just looks different. So what is a heat exchanger? Heat exchanger is number 8, and heat exchanger is number 10 on slide number 13. But all your key components are there. Number 5 is your king valve. Number 15 is your receiver. And then I asked the question, where is your dryer and your sight glass going in relationship to your receiver? The answer is after. It's downflow. It's downstream, right? So we're going to have our dryer first, and then we're going to have our receiver. Then we're going to have our sight glass. I don't think I said sight glass. I think I said receiver twice there. But your sight glass, number 7, your dryer before that. The purpose of your sight glass, detect moisture in the system, ensure proper charge. We want to make sure we have a full sight glass. We want a full column of liquid going to our metering device, which if we have a receiver, our metering device is going to be adjustable. It's going to be modulating, right? Okay, we shift gears. That's basically all we're going to talk about with receivers. The receiver is a storage device. It's taking in refrigerant and it's letting it out as needed. It's only letting out liquid. Our accumulator is letting out vapor. So make sure you understand that about that. Look at these slides, study these slides, and you'll be good to go there. All right, now we change to slide number 14. Aren't you glad there's only 36 slides today? We're going to spend quite a bit of time talking about the electrical side of it. This is something that is better practiced sometimes than preached. I can't remember. I heard somebody say it recently. I can't remember how they put it. But basically, the tone of it was, it's easy to preach and hard to it's easy to preach and hard to practice. We can look at pictures of electrical, but until you deal with it, it's still challenging. And we're going to talk about typical wiring diagrams on a residential air conditioner, slide number 14. We're going to talk about disconnects first. 15. There's no disconnect. I think I took this picture. I'm not sure. I think I lived it. But what you see on that picture is no disconnect and a very, very ugly line set. So the purpose of a disconnect is the same as, imagine you walk over to any appliance that's cord and plug. It has a cord and it plugs into the wall. Imagine you walk over to any of those appliances and grab it and pull it out of the wall. You pull the cord out of the outlet. That's a means of disconnect. You just disconnected that piece of equipment. That is typically, well, that is what a disconnect is. A disconnect is just simply a way to disconnect power from that piece of equipment. The purpose of a disconnect is for the serviceman to be able to work on it safely. That's the purpose of a disconnect. You can also, if you have to, you have to, and I don't know have to, but there are circumstances where you may have a fuse disconnect. Last I checked, as an example, I put an air conditioner in. It's a 14 SEER air conditioner. I take out a 10 SEER air conditioner. The 10 SEER air conditioner needed 40 amps of maximum overcurrent protection. Maximum overcurrent protection. What is that, Aaron? The breaker size, the fuse size. Okay, so the maximum amount of current that is permitted to go to that appliance per the label on the side of the unit that the manufacturer puts there on that particular one, as an example, is 40 amps. Okay, so it's got a 40 amp breaker inside. It's got wire rated to handle 40 amps of power, 220 volts, to the outdoor unit, but it also has a disconnect outside. Pardon me. New appliance only needs a 30 amp breaker. So what would I do in that circumstance most of the time? What I would do, so I got a 40 amp wire, I need 30 amp means of overcurrent protection, meaning where you're not going to have more than 30 amps going to that appliance. All the amps can go to that appliance at the breaker box. At the breaker box, there's no overcurrent protection on what comes in. Okay, I've got a 200 amp service. There's 200 amps. If I put a 300 amp load on the bus bar in there somehow, will it pull it? Yes, until it blows fuses that are up the line on the transformer, most likely. So my breaker box does a couple things. It's a distribution of power, but it's also a means by which I can throttle, I can hourglass down how much current will actually go through a particular wire. So I have a 40 amp wire, I have a 40 amp breaker. I'm only going to allow 240 volts, 40 amps to go through my wire to my disconnect to my appliance. I need a 30 amp max amp breaker somewhere in that circuit. I can technically use my disconnect and put a 30 amp breaker at my disconnect and still be okay, because my wire is 40 amp, my breaker upstream is 40 amp, but my breaker closest to my appliance is 30. So I am not an electrician. I play one on TV at times, but as of last I knew code, that is permitted. Because is my appliance getting more current than it should? No. But that disconnect is technically no longer just a disconnect. It's also it has the overcurrent protection in it. So ideally in that world, if I can get to my breaker box and I can change out that 40 amp breaker for a 30 amp breaker, that's the best thing to do. Can I also fuse my breaker, my disconnect, fuse or put a breaker there that accomplishes what needs to be done as far as my air conditioner goes? I can, and to my knowledge, at the moment, I believe that's still code, because we're protected on that circuit that goes to my disconnect. But at my disconnect, downstream of my disconnect is my appliance, and it's going to be protected by 30 amps. Sorry, a little bit of a rabbit trail there. That's just a couple things you can do with the disconnect. A disconnect is mainly, just imagine you're unplugging the cord out of a receptacle. That's the purpose, is to be able to shut the power off. It's supposed to be outside with the appliance. It's supposed to be not behind the appliance. It's supposed to, by code, be above snow grade. So, our average snowfall, we may have 10 inches, so you need to be above 10 inches on your disconnect. Typically, that's not too big of an issue, but it's going to mount on the side of the building typically. It's going to, you do not want it to be behind the appliance. Why? So that the workman can quickly get to it, shut it off, and be safe. More information you really wanted on that. All right, let's look at some slides here. Slide 16. Uh, you have a fuse disconnect. I think I got a little better picture here, so let's go to 17. 17. I love how that red wire stretched across there. What terminology you need to understand about a disconnect is load and line. Line, I cannot see it on that picture. Maybe if I zoomed a little closer in, I might. But on line, or even on slide number 16, let's look at that. You want your wires at the top are line wires, meaning your power coming in to your unit Nope, I'm backwards on that. Your wires on the top on slide number 16, your red and your black are your load. So they are going to your air conditioner. They're the load wires. Your line wires are in the bottom. They are coming from your breaker box. I don't know where else they've been, but there may be a junction box, there may be other things going on. There may be a sub panel. But these, your bottom wires here, are the wires that are coming in from your power source, your Vectron, through a transformer, through a main panel, through a breaker, to your disconnect, are on the bottom on this one. They would be labeled line. Your ones on the top, which are going to whatever's doing work, a light bulb, a refrigerator, an air conditioner, your load. Okay, so you can sometimes reverse these and it won't make a difference, but it's still not right. Typically, correctly, your line are the ones coming in, your load are the ones going out, and that's important to remember about a disconnect. There's a couple types: pull out and breaker type. Number 18 shows you pull out. On a pull out one, typically, if you flip it upside down and you can slide it back in, nothing makes contact, and it's off. If you flip it back over so that on says on, not no, it's on. When it says no, it's off. If it's the way it is, if it's like it should be. But that's slide number 18. I'm not a big fan of these disconnect. They're inexpensive. People can walk away with the pull out that you see there that the guy's holding in picture number 3 on slide 18. Then you got to figure out, you got to go find one, which can be a pain. That's a non-fused type of disconnect. Number 16 is a fused disconnect. They're pretty rare on most things anymore. Unless your customer buys the disconnect himself, he's going to go to Menards, and the only ones they carry are fused. Because you save big money at Menards. Okay, 19, you got a fused disconnect. Basically, you just pull that out, and the power's gone. 20, fused disconnect. Those fuses sit in those spades. There's supposed to be a fuse in there, not pieces of copper tubing. Number 21, my favorite type of disconnect for a couple of reasons, but this is a disconnect with a breaker on it. This is a square D, common as dirt, about a $21 to $25 disconnect. And to shut this unit off or turn it on, you simply flip the breaker. This breaker is not really a breaker, though. It's not an overcurrent protection device. How do I know that? Well, you can put an overcurrent protection device right in there. You can put a 30 amp breaker right in that spot on that picture in 21. If I look at this particular breaker and I look at the trip point, the spot that you flip up and down, there's a letter on, there's numbers on there. 30, 60, 25, whatever. Typically not 25. But 30, 60, 20, 40, that's the amperage that that particular breaker is rated at. If you come to a breaker and it doesn't have a rating on it, it'll trip at some point It's just not, that's not what it's for. It's a means of disconnect. It's a switch. It's not meant for overcurrent. A lot of times they'll either come, they won't have anything on them, or they'll be 60 amp. Typically, when you buy one of these, it's 60 amp. So if you're popping this breaker, you're pulling 60 amps. Um, Again, if you look at this picture, page 21, you have on the very, if you look at the breaker, to the left of the breaker up, there's a silver uh, lug, okay? There's one on the other side. Those are your line voltage, your line coming in. The power coming in is connected to your outer two lugs. And you can kind of see it goes in, and there's two little fins or kind of curves in. And that's where the power is connected to the top, if you will, upper part of the breaker. The lower part of the breaker is your load part. So when you turn the breaker on, your load is now active if it's working properly. Okay, that's what's going on with your disconnect. So you get up to a situation, had one Friday. We get all ready to test an air conditioner out. We turn the breaker on at the air handler. It won't do anything. Blower's not running. Nothing's happening. So I check the voltage going into two different breakers, 1, 2, right next to each other. 240 volts. Okay. Check the one breaker. 240 volts. Check the one next to it. Nothing. And you can feel when you're flipping the breaker itself, it just doesn't feel right. And what was wrong with that situation was that breaker had failed. I'd turn it on and off a couple times sometimes, and that's the thing that I don't like about these particular forms of disconnect is there are times when these breakers fail. So you need to make sure that you have a breaker in your truck to replace them because they do fail. I've had them. I'm in the middle of maintenance. I'm almost done the maintenance. Last thing I have to do at the house, and I shut the unit off and I turn it back on, and it won't turn on anymore because that breaker's just failed internally. Well, what's going on? Well, there's contacts in there that connect from my line to my load, right? I've got to make 240 volts, 120, 120. Actually, it's up here. These are my line. My load's down here, but when I click that breaker, it makes those contacts. Well, if something breaks off on there, this is typically what happens, not always, but typically I'll measure on this line here, I have 120 volts to ground. Across here, I measure from here to here, I have 120. I measure this to ground, I have 120. Well, I need to have 240, not 120. What happens is this one will fail and this one will still be connected. And that's pretty common. This one and the one on Friday both just failed. I had no power on that particular breaker, so I replaced the breaker and we were back in business. So that's the downfall of these. The reason I like this is because when I turn it off, it's off. When I turn it on, it's all the way on. On the push-in kind, you need to make sure you get it lined up and you push it in quick. Because if you push it in slowly, you can turn your compressor on, then you turn your compressor off because you lose power because you're making and breaking that connection. And now I've got a compressor that's short cycled, and I hate to hear that compressor short cycle. So that's something you don't want to do. Mainly, you just be careful, or just shut your 24 volts off, pull a 24 volts off of your contact or something like that, so that when you push that in, it doesn't start. Or if you're just careful, it's hard. That's why I don't like it, because if you can touch it and it'll turn the compressor on, then you don't get it all the way in all the way. Your compressor may not turn right back on. It might actually kick out on overload simply because you didn't push that disconnecting quickly enough. So that's the downfall of the push-in type. They're cheap. That's the best. That's why everybody uses them. The downfall of the breaker type is the breakers fail eventually, just from use. Slide number 22. This is more of a commercial industrial type of breaker box. Typically on this box, you cannot open the box to see the fuses or whatever's inside unless it's off. All right, wiring. Here we go. Number 23. Number 23, you got your components here. Real simple. We've got a fan, a contactor, and a compressor, and our disconnect. So what we're going to do is we have a ground. That's your green wire from your disconnect to somewhere typically on the frame or the metallic part of the outdoor unit. You've got a black going to your relay. You got a red going to your relay. We can call these L1 and L2. And from L1 to L2, we go to our on the outside on the inlet outlet of your contactor, if you will. Your line going in, and then going to your load. Your load is the side where your compressor and your condenser are. You've got 240 volts going to both. You'll notice on your compressor that you've got a V where it's wiring off, where you have L1 going to your common on your compressor. You got to start and run, and they're separate. It's the same line, L1, let's say, it's red, going to our compressor, and we'll discuss that at a later point. So when our contactor makes, the contactor makes, okay, open, close, your power makes, your compressor is going to have power, 240 volts, and your motor's going to have, your fan motor's going to have 240 volts, and they're all going to run, and everything's going to do what it's supposed to do. So that is slide number 24, 25. Another picture, everything's missing there as far as wiring connection, but you see your run, your start, your common on your compressor, which we'll talk about next week. That's 25, 26 wires connected to there. Something missing here, and we'll add that in just a minute, but the simplicity is there's where you see on your compressor terminals, you've got that, your red is forked off two ways. It's going to run, it's going to start. That's L1 is your red, L2 is your black. Does it matter the color and the delineation? Not really. You just need to make sure that you know which ones are L1 and which ones are L2. Because it's 120 volts, 120 volts. When that 120 volts, both 120 volts go to that motor, you have 240 volts. Well, how come that's not a dead short? Because you have sine waves, right? So you're alternating current. So that is why they don't dead short, because you have, basically you have two sine, there I go, I could be dancing. You have one sine wave, 120 volts. And in tandem, you have another 120 volts. I can't do this, I'm probably not coordinated enough. So they're cycling positive, negative, opposite of one another continuously, okay? So that's how that works. Same thing with your fan motor here. Only difference is here you have just two wires. Boom. There'll be a contact, or not a contactor, capacitor, and I believe we'll add that here in subsequent slides. Also notice you've got your compressor, or not your compressor, your thermostat. You got a yellow wire. You got here it's a black wire. Okay. What's happening is your thermostat, 24 volts is coming in, and you're sending 24 volts to wherever it needs to go. If you want to turn the heat on, you're going to send 24 volts to the white. If you're going to turn your air conditioner on, you're going to send 24 volts to your yellow. And typically, you're going to also send 24 volts to your green. Modern stuff, you may only do yellow, and then your green is made at your control board on your furnace, or your thermostat doesn't know that. It's still going to send 24 volts through green as well. And the board's going to be smart enough to know that, okay, yeah, we're making a call for Y, so we're going to turn on our cooling fan speed. So I'm on 26, now I'm on slide number 27. 27, we're just simply adding pardon me, we're adding two capacitors. Everything's pretty much the same here as number 25, except for we've added two capacitors. You'll notice on our condenser fan motor, we have a capacitor separated there. So you got a line and a frowny face is your symbol, right? Right next to your condenser fan on that slide. That indicates that it's a capacitor. We've discussed that when we did our troubleshooting walkthrough that we did here a couple weeks ago. Your capacitor gives the motor oomph to start. It's rated in numeric. It has a numeric rating in microfarads. So fan motor may have a 5 microfarad capacitor, 10 microfarad, 15, 12, 12.5 typically, 7.5. You've got a capacitor there. A capacitor needs to be good. if that capacitor is not good, your fan may not start. You may be able to walk up to that fan motor, take a stick, and push the fan to get the fan rotating. The fan will come up to speed and run. Why? Because you gave it to start physically. You were the capacitor in that particular moment. So you've got a capacitor here on this particular motor. They've got two brown wires coming off. What you'll see in the field, if you were doing this, you see a brown and white, and they're going to go directly to your fan capacitor. Typically, getting a little ahead of ourselves with wire colors. Notice on your compressor, you've got a run capacitor on what terminal? Can't hear you. Oh, it's on start. You're right. Why is our run capacitor on start? That doesn't make any sense. It doesn't. It's kind of goofy and messes with our hedges a little bit, but that's where it's supposed to be. Okay. Our run capacitor is going to break our start circuit. Okay. So that is where it lives. And that's kind of counterintuitive, but that's the way it works. When we start a compressor, basically where you will have problems and you will self-destruct a compressor is if you have power to run and start simultaneously, continuously. And we'll get into that next week. You don't want that. So we need that start winding to be in milliseconds just to get the start. Motor starts rotating, great. Run takes over. In this particular picture, what's going to happen is you will still have a little bit of voltage going to your start winding. It's trickled to it. How? Through your run capacitor. Okay. So that's what's going on there with that. There's your run capacitor. In all we added, as you see on the slide in 27, is two run capacitors. Our thermostat stuff is still the same. 24 volts to the thermostat through our red wire. Then the thermostat switch makes, and now we have 24 volts coming in and going out through our yellow wire. Goes to our yellow wire, through our yellow wire. It's probably going to stop at the furnace and be connected to a yellow wire that goes outside. That yellow wire outside is going to connect as you see on your contactor, your 24 volt coil. That coil won't work unless we have a wire going back, right? We have to have a neutral. We have to have a common. We have to make a circuit, right? It has to start and it has to end. If the circle doesn't come back to itself, if the circle is broken, unlike the song, will the circle be unbroken, right? If the circle is broken, the current stop, the electrons stop. They can't go any further and nothing happens. When we make that, we have a load here. Imagine a load. Okay, that's a light bulb, if you will. The power comes to the light bulb, and then it has to have a path back. That path back is your neutral or your common on your 24 volt. Where are we at? 28. Up to 28, we added a couple things here. High pressure, low pressure safeties. All we're doing is breaking, made, the light bulb's on. Broke, the light bulb's off. Okay? You have a high pressure and a low pressure switch that were added. What are they doing? Well, the high pressure switch, if the pressure gets too high, it's going to open. On 410A, it's probably going to be like 600, 625 maybe. So if the pressure inside that system gets to 625, that switch is going to open. What happens then? The contactor opens. What happens then? There's no power to our compressor that's downrange or our fan motor that's downrange. None of that stuff's going to run. Why? Because the power's been shut off. So pressure goes back down. Our switch makes, our contactor makes, our compressor comes on, our fan comes back on. They're running, and some kid comes along and hits the liquid line with a hedge trimmer and blows all the refrigerant out. Well, the high pressure switch is going to stay closed. The low pressure switch now gets below 40 psi. Boom, it opens. What happens then? Well, the electrons can't jump across this gap. So your contactor opens as well. So it shuts the power off to your compressor, to your fan. They're not going to work. Why? Because because the 240 volts is gone. It's gone. It's still on your line side of your contactor, but it's not on your load side of your contactor. Why is it not on the load side? Because the contactor switch on the switch on the contactor is open because there's no 24 volts there. Why is there no 24 volts there? Because the thermostat's off? No, thermostat's still asking for cooling. Your high pressure switch is still closed, but your low pressure switch is open. So your low pressure switch is just simply a safety that if something happens to the charge, we're low on refrigerant, the charge got blown, whatever happened, that low pressure switch opens and our electrons can't flow and the work doesn't get done. The load side of the circuit doesn't have power because our contactor is open. All right, I want to be careful. I want you to understand the electrical side because 75% of this stuff is electrical. Remember, there's there's more than this, but in general, when you're starting out and trying to figure out, okay, how do I wire something? How do I deal with something as far as electrically to understand what I have? You need to understand where the component is a switch, okay, on or off. That's all it does. If the power is over here and it's made, it's going to go through. Okay, pretty simplistic. If the power is over here and it's made, it's going to go through. So on a switch, I tell you, me and my arms today, man. It doesn't matter on a switch which way I wire it. Okay, when you wire a switch, it's open or closed. Typically, because there's going to be some weird one out there, but for the most part, it doesn't matter which side of that switch you hook your wires to. It's just a switch. So if you look at that picture, look at slide number 28. You've got your high and your low. Your high and your low are just switches, open and closed. That's all they do. They're switches. Now look at your compressor. Look at your condenser fan motor. Do they do work? Yes. You know, the motor inside goes round and round. The fan goes round and round. So it's doing work. So they're loads. They consume energy. So a load should have an amp draw. A light bulb is going to have an amp draw. Anything that is a load is going to have an amp draw, and it's going to have something else that makes it different as far as wiring goes. It has to have a way for the power to get back, okay, back to our circuit. Okay, power comes in, hits our load, and goes back. Back to my light bulb. This is a letter opener. That's what's going on there. On a switch, it's just two wires, okay, in and out. Now you can have switches where you have all kinds of wires going to it because you can have switches on top of switches on top of switches. You can have them stacked or different configurations. But at the end of the day, it doesn't matter. It's just open and close. Okay. Now what makes it open and close, you need to understand. But on a switch, it's the same wire. Okay. There's no difference in the wire. Okay. It's one wire. It's the hot typically. Well, not typically. You always want to switch your hot. Okay. You never want to switch your neutral or your common. What's the difference between neutral and common? Wrong class. We really don't have time to go into that. At the end of the day, what it really is, it's just the other way. It's got to have a way back. Remember when you had one of those race cars you got for Christmas with the trigger on it, and you put it on that black track that you snapped all together, and you plug in the transformer in the wall, and you got a cord, and you got the trigger. Slot cars, sometimes what they're called. And that car goes round and round and round and round and round until you pull the trigger too far and it blows off the corner, right? Put the car back on the track, and if something happens and that track is not snapped together correctly, the car won't work. Why? Because there's no circuit being completed. No circuit. Round, okay? It's gotta go in, gotta go through our load and then go back. And on any load, you're going to have a neutral or a common. So if you look at your relay, you got a yellow going in one side of your relay, it's a load. The 24 volt coil on your, I'm sorry, not relay, contactor. If you look at your picture, you got your contactor there, and then you have a 24 volt coil. That's a load. So that load has a wire going back. In my world, I like that wire to be blue. I use blue for my neutrals, for my common. That's my 24 volt, two sides of your 24 volt. Not really, but it is. It's a hot and a common. There's two sides. Okay. One I worked on the other day, it had a red on your secondary side of your transformer, which is 24 volts. You had a red wire and a gray wire. And their gray wire they were using for common, the red wire they were using for hot. All right. Anytime you have a load, you have to have both. So you walk over and you plug something into that receptacle. Again, that receptacle has 120 volts going up to it, typically on a black wire, and it's got a white wire that they're calling a neutral. That white wire allows the electrons to travel back to your breaker box. You have to have a complete circuit or it won't work. If you disconnect the white wire, the refrigerator is not going to work. The ice maker is not going to work. Whatever you plug into it is not going to work because you don't have a complete circuit. Okay, so that's what I want you to think about when you're thinking about electrical stuff. Is it a load or is it a switch? Because it's going to affect how you test it and what you're looking for. Okay, because I can take my high and my low here. I can disconnect from my high and plug that right into the contactor. And I've just bypassed my high and my low switch. And I can see if the system starts up. So I can see if the compressor's good. I don't have to do anything with any other wires. Why? Because it's just a switch. In a load type situation, if I want to isolate that, I need to really the best way to do it, the way to really isolate that component, you have to just disconnect both of your wires. In this case, 240 volts, in order to isolate it to test it. So that's important stuff that you need to understand and think about. Well, how am I going to test for 24 volts? Do I test from 24 volts to the metallic ground on the outdoor unit? Nope. Voltage is the relationship, the difference. Okay, it's the difference of sorry if I want to say it that way. It is. It's the difference of potential. Okay, so there has to be a difference between the 2 points. So imagine, look at your switch there, your high switch there. You got a yellow wire coming in, yellow wire going out. If I check for voltage right now across that switch is in a closed position in the picture, how many volts will I measure? None. 0 volts. What does that tell me about that switch? It tells me that that switch is closed. Imagine the cuffs on my jacket are my 2 points where I have my terminal, my probes for my voltmeter are connected on my cuffs. Okay, there's no difference electrically between those 2 points. They're the same. There is no difference. If I take my tongue and I touch this wire, I will get shocked if there's power there. Why? You measured 0 volts. Well, because there's no difference in potential between these 2 points. Now what am I going to measure? I'm going to measure line voltage when the switch is open. I'm going to measure 0 when the switch is closed, because there is a difference between these two. The electrons will travel through your probes to back to wherever they have to, and they're going to notice, okay, there's a difference between where this one's connected and where this one's connected, because they're no longer made. When they're made, it's going to see 0. When they're broke, it's going to see line voltage. That's how you test a switch. That's very important. Okay. It doesn't do you any good to have a meter if you don't know how to use it. Whenever we're looking for 24 volts, you need to find a common. What do you mean common, Aaron? Back to your neutral or your common on your secondary 24 volt side. That blue wire, as I point to the black wire, the black dotted wire, dotted meaning it's low voltage. Okay. Your black wire, which is called your 24 volt common from transformer on the PowerPoint. You want to connect it to there. Just leave it there. Clip it on, alligator clip it on there, and then go out and test your stuff that you want to test. Put it on the other side of the coil. Do I have 24 volts here? No, I don't. Okay. Go up to your outlet on your low voltage. No, I don't. Okay. go to the inlet on your low pressure, not low voltage, low pressure switch. I'm referring to the switch here. Okay. So I've tested at my contactor. I've landed my 24 my one probe on my voltage meter to my black dotted line, slide number 28 on my contactor. It's there. It's stuck there. It's not going anywhere because I want to measure difference of potential in voltage, AC. I touch it to the coil, other side of the coil where my yellow wire is. I have 0. Okay, so there's no voltage there. All the way back to my transformer, there's no voltage. There's no difference here. Okay, go up to my low pressure switch, go to the outlet side. Okay, the side on this way. Touch there, 0 volts. Okay, go to the inlet side of your low. Ding, 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 ding. I now have 24 volts. So I now know that switch is open. I got 24 volts at my low inlet. I have 0 volts to my back to my transformer on my common side. I have 0 volts on the outlet. So my low side pressure switch is open. So kind of belaboring that a little bit, but I want you to understand and think about, okay, how do I use my meter? Because it's very important. You just if you put those probes in the wrong spot, you're not going to get the information you need. You're not going to be really doing anything. And I'll come back to that. We'll scroll up and look at a couple of things here in a minute. Number 29. All we have there, the difference is we've made our contactor. There's 24 volts. You see the lightning coming out of our 24 volt coil there. It's actually on. Okay. Number 30, 29, 30. Oh, your high voltage, your high pressure switch is open. 31, we added an oil pressure safety switch. Your crankcase pressure is the same as your suction side pressure, which is the same as your oil pressure. 32, we've just added everything all together in a normal situation. It says, typical wiring diagram of a residential AC unit. I've never seen an AC unit with an oil pressure switch, but it's there. And here's the one thing you need to remember. You will have a wiring diagram on that outdoor condensing unit. It will show all kinds of components. You may not have those components on that unit. They print one wiring diagram with all the stuff on it, and they may ship you something that doesn't have all the stuff on it because you didn't pay for the extra features. But they just print all those things on there. They may or may not be in that unit, but if they are, you have it. If they aren't, you have it. That's just kind of the way they do it. 33. Again, saying you don't need to know this for your exam, but this is big important stuff. I'm not going to test you on these wires and where they're located, but I want you to understand what's going on here. 34, we've seen a picture very much like this in when we walk through this stuff together. You will see, well, we're not going to deal with that at this point. But there's your parts labeled in 35. Now, before we're done, it's time to be done. But let me go back up here. Go back up with me, if you will, to, let's pick a good one. I kind of said this before, but I want to go over it one more time really quickly with you. We're back in the 1920, that range. Go to, I'm on number 17. The thing I really dislike about this slide is how that red wire is stretched. The outer two as it says, wires feeding to the air conditioner. So those are going to be your load. The inner two are going to be your line. So real quick, while we're on voltage, while we're on using a meter, so I want to check for voltage to my unit. I get out on a call, there's nothing happening. Okay, the disconnect is pushed in. In this situation, there's a plastic cover that covers all those wires right above the top of this picture, right above where your terminals are all landed there on those 4 lugs. That is where the push-in disconnect is. Let's say that that's in. All right. and we don't have any power, and we're trying to figure out what's going on. How am I going to connect my probes to figure out if I have 240 volts outside? As I said, your inner two lugs, your inner black and your inner white, there are your power coming to the disconnect. So I should have 240 volts there. So if I take my probe 1 and probe 2 and I connect it to the inner two lugs, my black one and my white one, touch them there, my meter is on AC voltage. I should measure somewhere between 208 and 230, okay? I'm going to measure on a residential house, I'm going to measure 238 volts off the top of my head, okay? 238 volts. So that's the difference between those 2 points is 120 on one, 120 on the other, 240, give or take, okay? So I know I have power going in to there. On my outer two lugs, my one with the red that's stretched and the black one, those two on the outer parts, same situation. AC voltage on my meter. Don't touch it with your hands, the bare parts where you're touching the probes. Touch there. I have 120 volts. Houston, we have a problem. You're not getting voltage off one of those legs through your disconnect. Your disconnect is your problem because to your disconnect, I have 240. Across those 2 points, I should not measure 120. I need to measure 240. Well, let's figure out which leg is bad. Okay, you got your black one to your right. One on the black one, that's your load side, your outer black one, to ground. I have 0. Okay. Now let's check the other one. Take that probe and go to your red one and you leave it on the ground. Boom, 120. So your red line, your red outer load, not line, your wire, your outer red wire has 120 volts on it. Your other one, difference to ground, is nothing. Really, you're probably not going to see that. You're more likely going to see like 6 or something really. It's never perfect, but you may see 4 or 6 volts. Well, that's nowhere near 120. Okay, so let's go back again. Take our probes. Take our 2 probes to our outer, okay, our outer black on one side, our outer red on the other. I still read 120 volts. Okay. I need 240 for this piece of machinery to run. So what's happened is most likely if you pull that disconnect and you look at the lugs inside, one of them's burnt or something's happened there. Something internally on that disconnect is bad. But you need to understand your L1 and L2 is what we're dealing with here. There needs to be 240 volts there total. Because there's a 120 volt difference between the two. The sum of that is 240. So if I go to my red to ground, I should read in that ground. If you look in the middle of your disconnect, there's a green wire and a bare wire. At the back middle of that disconnect on slide number 17, from red to ground, 120. From black to ground, black to ground on the other side, 120. Measure outer on both of the upper lugs, outer corners, the black and the red, 240 volts. Okay, it's really important because sometimes we think we know how to read a meter and we don't, and it'll get us in trouble. Okay, spent a lot of time with you today. If you have any questions, please email me, call me, text me, and I'll be glad to help you as I can with what I need to help you with. But that's more or less, like again, have any questions, please let me know. I'm going to make these available to you so that you can watch the videos. And take care. Again, if you have questions, give us a call. Thanks. Bye.